Hi there. In this video I'll be taking a look at Penetrator, the Commander X16 version. It's the making of, and it's a technical overview, but not a detailed technical view, more of a high-level overview of how things work in this game. So for the purposes of this video, I've broken things up into the 5 main points: the infrastructure, which is the underlying memory management buffer type stuff, the terrain rendering, sprites and sprite rendering, one slide about text, and then just some closing remarks. I'll start with how Vera is configured. Other than the very first intro image that you see, which is done in 4 bits per pixel, the rest of the game is done at 2 bits per pixel. The intro image uses 7 or 8 colors, and so needed 4 bits per pixel. The rest of the game I can manage with 2 bits per pixel and only 4 colors on screen at any one time. And so the resolution is set up, I'll speak in terms of text columns. So you can just poke this in BASIC yourself and see 40 columns wide, 40 text columns wide, which gives me 80 bytes per screen across, and then text rows are approximately 23 rows down during gameplay and 29 rows in the UI. And the reason these two differ is that at 23 rows down, you get some artifacting with especially the font. It is noticeable, but you'll see it sometimes on different lines. The bullets look as though they're 2 rows high, 2 pixels high, and sometimes they look like they're 1 pixel high. And that's just an artifact in the scaling. So that at 29 rows high, everything looks crisp and clear, and the font looks good and smooth. And then the game doesn't actually use the layers in any sort of a text mode. Everything is drawn to it as bitmap, in a bitmap format. The way this works then is with this draw present function, which basically hides one layer while it shows a second layer. And the variable I keep track of this is called the back layer, because from a making standpoint, you're only interested in the back layer, the layer that is hidden, because that's the active layer for drawing. And once you've done your drawing, at the end of the frame, you call this draw present, and it hides the front layer that was visible to the user and unhides the back layer that you just drew to, and therefore you get the smooth animation. The VSync happens because this game is so fast compared to what would have happened on a Spectrum that there's quite a bit of time that you're just sitting around waiting so that the frame rate would match, or the execution rate would match that of the Spectrum for playing, and how fast things scroll and things move and so on. And so I just sit and watch the fastest bit of the timer, which appears to me to be approximately 16 milliseconds. I think I saw somewhere it might be 20 milliseconds, I'm not sure. But anyways, so that I wait for, and that is incremented in the IRQ or the VBlank. And so when that changes, I sort of get free VBlanking with that. The game very heavily relies on 6 256 byte buffers, and the reason they are 256 bytes is that that's, for an 8-bit machine, a natural circular buffer. So if you use an index register, let's say X, and you increment X and it goes over the end, it automatically goes to 0, and if you decrement X from 0, it goes to FF, which happens to be the end of the buffer. So there is no math required at all to manage these buffers. And even though the screen is only 80 characters wide, I still use these 256 byte buffers just because it's so convenient. And so these buffers are the world T buffer, which is the top buffer, and that contains the height of the world at the top for every byte. So for every 4 pixels there is a height. Same for the world B buffer, that's the bottom. The enemy buffer says where the enemy sprites are in the world. The height buffer says how high an enemy sprite is in the world. So the height buffer is generally set to the world height -1, but if the enemy is flying, then the height buffer says at what height the enemy now is. The bullets buffer is the same. It's the bullets traveling. It's a little bit different, but I will get to that later. And the explosion buffer is just where the explosions are happening. And then there are indices that run across all of these buffers. Well, the bullets buffer is the one that's different, but the buffer insert point is, think of that as the right-hand column of the screen, and the buffer draw is the left-hand edge of the screen. And the bullet index is where in the bullets buffer to start drawing. So what makes the bullet index different is the others are incremented, buffer index and buffer insert and buffer draw, but bullet index is decremented so that the bullets move to the right. Every time I draw the bullets from bullet index and I decremented it, obviously the bullets are one more cell over to the right. This slide explains it all a little bit more clearly. So the two cells at the top, -1 and 80, they are the off the screen left edge and right edge of the screen, and then 0 to 79 are the on-screen columns. And so the buffers, the buffer draw and buffer index are at n and n plus 80. And of course, n is then this thing that runs through the 256 byte buffer, incrementing every frame. Same for the buffer index. And then the will T buffer will contain values. So let's just say that they are hex 8888. 8 means it's above the top of the screen. You don't draw. The will B buffer is the bottom. It has a few values. And so what will happen is that the terrain will be rendered from those two buffers into the screen columns. In the terrain's case, starting at the -1 off-screen column and going through all the way to the buffer index up to column 79. So the terrain data is stored in this triplet format, where the first byte is the bottom height of the terrain, the second byte is the top height, and then the third byte is a flags byte. And the flags have the following meaning. 0 means there's nothing going on. 1 is insert a missile at this point. 2, insert a radar at this point. And hex 40 is the change of stage. So going from 1 to 2, or when you're flying in reverse, from 2 to 1. There are 7,002, I think, if I remember correctly, bytes of this terrain data stored in this triplet format. So the way it all comes together is then through two functions. The first is terrain show, and the other one is to terrain draw a column. Terrain show will start by clearing the portion of the screen where the terrain will be drawn, which also includes then, it's a bulk clear, like a whole section of the screen. So the sprites and everything from the previous run is completely erased, and then it redraws the terrain. And as I explained a little bit before, it starts off of the left edge with the last written values, which are off screen, and then it steps onto the screen and just runs through from buffer draw all the way to buffer insert, writing new values into the terrain. And terrain show basically preps the two previously drawn buffers and then calls terrain draw column, which literally just draws one of these screen columns. It's a very, very simple way of doing things. The way things are done in this game, as in the original, is that a column is 4 pixels wide. So when the screen scrolls from right to left, it scrolls at 4 pixels at a time. When the terrain goes up or down, it actually takes a 4 pixel column to do that. So in the right hand side of the screen, you can see some X's. That is a typical terrain piece. And so what happens is that terrain draw column will set Vera up with the high bits of 0, 0, so no stepping, and it will write in from the previous column at the height 2 pixels. Those are the two at the very bottom. Let's say this is for an updraw. It'll write in 2 pixels, and then it'll start looping until the height is the height that it desires, writing in a single pixel, except for the very last, so one less than it desires. And then it'll write this pixel on the far right hand side at the height that it is, and that'll connect to the next cell. The next cell will then start directly to the right of that and write 2 pixels or 4 pixels if it's straight through, or 2 and then an up row, or 2 and a down row, and that is it. It's very, very simple. It processes it one column at a time. And what makes this on the Vera so much easier than what it would have been on the ZX Spectrum is that on the Spectrum, at single bit per pixel values, you'd have to, on the way, let's say that you had another column going down to the right of that, you'd have to read this byte again and or in the value that you'd want and then write that again. So it would be quite a bit more intensive than what I have to do on the CX16, because I can just write these columns. Since it is 2 bits per pixel, 1 byte is 4 pixels, and it just works out perfectly. Magical. The last step that makes the terrain rendering and scrolling then work is game world move. And all it does is move the insert point 1 to the right through those 256 byte buffers. And there is a 0-page pointer called Z world pointer, which points into this triplet data stream in the world. It moves that along by 3 bytes and then reads these 3 bytes. The first byte is the bottom byte, and that gets written into the world B buffer. Second byte is the top byte, that gets written into the world T buffer. And the third byte is an enemy flags byte, and that is 1 for a missile and 2 for a radar. And if it is 0, it's nothing and it just moves on. And if it's either 1 or 2, it'll call game world flags to set up the sprite renderings. And so that's a good way to segue into sprites. We'll start talking about sprites by looking at sprite data, and what you see here genuinely is my sprite editing tool. I know it seems a bit absurd, but it works really well. So at the top in the cyan color you see a bunch of data that is literally cut from my working assembly file and just paste it in there, and that generates the first image at the top of the red data. Since there's a bit of a formula to get that data there, I don't want to overwrite it, so the second one down below is simply a copy of the top, and I can then easily overwrite it and change it, and that generates the data at the bottom that the green points out that I can just, it's all in a single column, I can just cut that column and paste it back in my code, and I've got the updated sprite data. So what you see here is 2 bits per pixel data, so you can see that the radar dish uses a 1-0 type data. The missile might use a 0-1, and then anything that needs collision, like the player ship, the bullets, the bombs, they will all use a 1-1 data format for the pixel, and that has to do with collision, which I will get to in a little while. The other important part is you'll see in purple I've highlighted the big column of the radar. That is a row of data in my data format, and that is because I render the sprites in columns, exactly like the terrain. And so I'm going to go in the next slides, I'm going to cover off how that works, but a sprite in my game isn't really a complete unit, it is actually a bunch of strips. To understand all of this a little bit better, I'm just going to explain the enemy buffer. When that game world flags routine populates the enemy buffer based on that third byte in the world data, 1 for a missile, 2 for radar, it makes a new byte that it inserts into the enemy buffer. And it doesn't necessarily make 1 byte, it makes 1 byte per column. So the nukes are 1 wide, the missile is 2 wide, the radar is 4 wide, and the monsters are 3 columns wide. And so each of these bytes, let's say for a missile where it inserts 2 bytes, each of these bytes would have the following format, where bits 1 and 2, I know that the convention is probably bits 0 to 7, but I in the code used bits 1 and 8, so I'm just going to stick with this convention. Bits 1 and 2 are the enemy type, and you can see there that a nuke is 00, missile 01, radar 10, and a monster 11. So that's in binary, so those are values 0, 1, 2, and 3. Those are the bottom 2 bits. The next 2 bits tell me what column number it is, and so that's what I said for the strip. The nuke uses only 0, 0 because it's 1 column, the missile uses 0 and 1 because it's 2 columns, the radar uses 0, 1, 2, and 3 because it's 4 columns, and the monster uses 0, 1, 2 because it's 3 columns. So those are the possible values for the strips. Bits 5 to 7 are mostly used for animation data, except for the monster. And basically it's 0 for a nuke because it has no animation frames, it's 0 and 1 for a missile because it just flip-flops between 2 frames, 0 to 7 for a radar because it has 8 frames of animation data, and then the monster uses bit 5 to say whether it's traveling up or down. 0, if the bit is 0 it's going up, if the bit is 1 it's going down, and bits 6 and 7 are a counter to tell it how long to hold. So if you have played the game, you'll notice that at the top of the world the monster sits still for a bit, and at the bottom of the world it sits still, and then when it passes by the player ship, it'll also sit still for a little while. And that's what those counters do. And then bit 8 says whether the enemy is still on the terrain or whether it's airborne. It makes a difference how much you score when you kill an airborne enemy versus a non-airborne enemy. So the missile, for example, you get a different score whether it's in the air or not. And yeah, that's basically, you do need to differentiate whether some things are flying. So the only flying things are the monster and the missile. So finally we get to draw sprite. So what draw sprite does is it sets up a stride of 0. I'm not sure, people I think have different names for it, but that's basically whether the thing advances or not when you write or read from data 0. So I set it so that it doesn't advance, and then I look up the sprite data and I EOR it with the Vera data 0. So I basically read from Vera, EOR the thing, write it back, and then I AND the value of the sprite with the value it was before the EOR, and if it's not the same value, then there was a collision. So in this little table, you will see the terrain is 04, the sprite is 0F, the XOR of that is 0B. If you AND them together, you get 0B. So in the top row where I've marked the red Y, that is a collision bit, and you'll see that the 0F and 0B and 0B is not 0F, it's 0B, so there was a collision. The next row down, you'll see 02, XOR with 04 is 07, you AND that with 02, and the answer is 02, which means that they touched each other, like side by side, but they did not overlap, so there was no collision. So it's a very, very simple system to determine whether you have collisions, and it is pixel accurate, and the Vera is absolutely fast enough to do this. So it does mean I have to set the Vera address for every single write of a sprite. It's actually a read and a write, but there is absolutely no problem with that. It is screamingly fast. Draw sprite can and does write across multiple columns. So the player's ship is 5 columns wide, the bombs are 2 columns wide, and you render those in a single go by saying render me 5 columns, and here's the start of the data. But for the most part, DrawSprite actually writes a single column, and that's because the enemies are now placed in this enemy buffer into different columns. So what would happen is you would see a byte, and it would say in the column that it is 00, 01, 02, and you would just load the index into the sprite data for that column and pass that to Vera, and it would just rip down all the rows of that column that has the sprite data and write it in. So it's very, very simple and straightforward. It's a tiny bit of code, works very well, is very fast. So the game kill enemy is a little bit more complicated, because when you have a collision with something, you have to go to the enemy buffer, look up the column number, figure out how far back the sprite actually started, and then erase those enemy bytes from the enemy buffer for the entire enemy. But it's not a lot of work, and I mean the advantage of this is that as a sprite disappears off the left-hand side of the screen, you don't need to realize that some part of it is still visible, because there is a byte in the enemy buffer that says this column is still on screen. And as the sprite scrolls in from the right-hand side, when I get the enemy flag, I put at enemy insert, let's say it's a radar, at enemy insert I put radar column 0, at enemy insert +1 I put radar column 1, etc. And so as enemy columns radar columns 0, 1, 2, and 3 come on screen, they just start rendering, and I don't have to worry about clipping or anything else at all. It's just right built into the system. So that's why I said this, the way that this Vera thing works at 2 bits per pixel is a perfect match for the game. It makes things so much simpler. The enemy height buffer is then the last buffer, which I've already spoken about. It's generally set to terrain height -1 when you encounter an enemy. It's always set to terrain height -1, in fact, when you encounter an enemy. And then as the in the air bit is set, the processing of the AI will move that sprite up or down and will change the enemy height buffer as needed. I've already mentioned the bullet buffer before, and that it moves in a different direction. The bullet index moves in a different direction. It's decremented. This is worth noting, though, that this bit me. I first had done the bullets going once and the terrain going once, and that worked really well. And then I realized that's not how the original game worked. I thought I understood how the original game worked. And then when I did a side-by-side comparison to see if the speed's right, I noticed that it's not at all right. And then I looked closely and I realized that the original game moved the bullets twice and the world once. And that you actually have to render you can't just move the bullet twice and the world once in a single frame. You actually have to have separate frames. And the reason is, if you look at the right hand side, if the bullet was in columns 1 and 2 and the world in column 3, and you move them all at the same time, the bullet would move from column 1 to column 3, so 2 columns, and the world would move from column 3 to column 2, and there would be no intersection. The bullet would cleanly pass through the wall, and that happened to me. So you have to render the bullet in column 1, then in column 2, and then in column 3, and you have to move the world during one of those 3 frames from column 3 to column 2, so that you do get a chance to have an intersection and have a collision. So that's the only thing that makes the bullets a little bit interesting, is that they actually force you to have, for one world move, 2 passes, 3 passes. So it's But again, it has no effect on frame rate. I suspect that on the Spectrum version, it might have actually been beneficial to only render the world, to only move the world once in a while, or maybe not. If he double buffered it, I guess maybe it made no difference. But anyways, it makes no difference to me in this game. Text is very simple and is very much rendered like a sprite, but there are a couple of things that make it worth mentioning. And the first is that the characters are 16 bits wide and 8 bytes high, so 8 rows high. And when rendering the text, it's possible to pass in a mask, as you can see in the image below, which allows you to clip out alternate columns, which then gives you the 4 colors. If you pass in a mask of all 0, you get the background color, and then the other 2 masks give you all the left bits or all the right bits on, or a mask of all ones gives you both columns on, and that's how you get the colors. So that's kind of a neat feature. And then there's this big text where it says bonus 1000 points. Wow. There's a plot function in the game as well, which can plot a block of pixels of a certain width and height, and they are always square, these pixels, just the way I wrote it. And so I spin through this font, and wherever I encounter a 1-bit, I plot a block of text, as a 4x4 or a 8x8 or whatever, and so that's how I do the large text. So it's actually genuinely done from the font as a large thing. You have very little control over kerning or anything else, so I sort of just made it work with needing to say those specific words. And that really brings us to the end of this overview. There's really nothing special going on. I think all credit must go to Philip Mitchell. He was obviously a very clever guy, making all of this work on the ZX Spectrum back in the day. I've documented the machine language, the assembly language code as much as I could, because I am not an old hand at writing assembly language, and I find it quite hard to read the code. So for my own sake, I had to document it. The documentation might in cases be a little bit out of date, as I realized I'd made mistakes and maybe used Visual Studio Code's global search and replace, and may not have gotten all the comments right again, but I think it's actually pretty good. And then the last closing remark is just this Dilbert comic. It wasn't exactly the one I was looking for. I found another one once, or I saw another one once, where Dilbert said, you guys start coding and I'll go figure out what it is that we're supposed to make. And this was a little bit how I approached this. I started coding before I should have, and I made several mistakes. I mentioned the bullets one, but I also drew the terrain straight from the terrain, and you can make that work, but it'll be quite a bit more work, and you'll have to have a separate terrain function for going backwards and so on. So I wish I had paid a little bit more attention to the great work that Philip Mitchell had done, because that would have saved me several days of plowing through old code to figure out how to fix it so that it would work the way it's supposed to work. Anyways, it was still a ton of fun to make. And if you have any questions, feel free to email or contact me. It's all in the GitHub page. It's GitHub is StubBC Penetrator is where the code is, as is in the other video. And if you're looking at this video, you obviously know where my YouTube channel is. All right, thanks for watching.